This video is on the properties of logarithms and covers material that's contained in section 5.5 of the textbook. Let's begin by looking at log base a of 1. And we want to know what this is equal to, so we'll say for now that it equals y. This corresponds to the exponential equation a to the y power equals 1. Well, we know that anything when raised to a power, if it equals 1, that means the power has to be 0. So this means that log base a of 1 is equal to 0, regardless of what the value of a is. Now let's look at log base a of a. Let's say that we set it equal to y. This corresponds to the exponential equation a to the y is equal to a. By inspection, we can say that y is equal to 1. So this means that we have log base a of a equals 1. Now let's look at an equation that's in the textbook. Log base a of a raised to the r power is equal to r. How can this be? Well, let's look at the equation carefully. When we have log base a of something, that means we can write the base, which is highlighted in red. And then we know that the log expression is equal to the exponent, which is highlighted in blue. So we now have a to the r. We're building the exponential equation. The final piece is the argument of the log function, here highlighted in green, a to the r. So we've built the corresponding exponential equation, and it shows that the two sides are identical. Now let's look at the equation log base a of m is equal to y. We can build an exponential function from this. A to the y is equal to m. One of the things that's true here is if we have two expressions that are equal to each other, here log base a of m is equal to y, we can take a base, here a, and raise it to the power that's on the left side of the equation, which is written in blue, and then say that that's equal to the base raised to the right-hand side of the equation, written in green. So now we have a to the log base a of m is equal to a to the y power. But then we also note, based on what we see in the first line on this slide, that a to the y is equal to m. So what this means really is that we can say that a to the log base a of m is m. That's a nice way to simplify something that looks pretty complicated on the left-hand side. Now let's look at some other properties of logarithmic functions. If we have the log of a product, we can express that as the sum of logs of the individual factors. So here we have log base a of the product m times n. That equals log base a of m plus log base a of n. Similarly, if we have log base a of a quotient, m over n, this is equal to log base a of the numerator, m, minus log base a of the denominator, n. Another useful expression is when we have log base a of m raised to the r power, this is equal to that power, r, multiplied by log base a of m. We can use all of these expressions, properties of logarithms to help simplify equations that have logs in them. So let's say we have an expression 2 raised to the log 2 of pi. That's supposed to be log 2 log base 2 of pi. Sorry about that. I didn't really format that very well. It's not log of 2 pi. It's log base 2 of pi. Based on the properties we've seen already, we can say that this is equal to pi because 2 is an exponential function. It's 2 raised to something. And log is the inverse function. So really, it's a function of an inverse function. And so what we wind up with when we simplify is the argument of the inner function, which is the log base 2. We simplify this and it comes out to be just plain old pi. Similarly, the natural log is an inverse function of e, the exponential, raised to a power, here kt. So if we take the natural log of e raised to the kt, we're simply going to get that exponent of e, kt. Another simplification we can do, if we have e raised to the r times the natural log of a, this is the same as e raised to the natural log of a and the whole thing raised to the r power. We can then simplify what's inside those large, because the e and the natural log are inverse functions of each other, and it simplifies again to the argument of the inner function here being the natural log, and we get a raised to the r power. Now let's say we have a quotient, a natural log of a quotient. We have the natural log of x squared divided by x minus 1 all cubed. We can simplify this by saying that this is equal to the natural log of x squared minus the natural log of x minus 1 cubed. So when we do this, we can then look more carefully and say, all right, this is great. We've taken one step forward, but now let's think about what x could be. We know that the argument for a natural log has to be positive. So the first term, the natural log of x squared, we only can put values in there that will be greater than 0. So that means that x would have to be greater than 0. The second term, in order to make what's in the brackets positive, x would have to be greater than 1. So if we take those two constraints, x has to be greater than 0, and x also has to be greater than 1, that comes out to mean x has to be greater than 1, and that's the overall constraint on the expression. So now we figured out what the domain is. Now we can simplify the expression further by just taking that square term, that x squared, and putting the 2 out front. So now we have 2 times the natural log of x. The second term simplifies by taking the cube that's within the natural log and putting it out front, again, using a simplification expression that we looked at earlier. So now we have 2 natural log of x minus 3 times the natural log of x minus 1, and x has to be greater than 1. And that's as simple as we can get this. Let's look at another expression. Let's say we have log base a of 7, and we want to add to that 4 times log base a of 3. To combine these, we have to make sure that the base used by the log is the same in each case, and it is. They're both a. So we can proceed. The first thing we're going to do is look at the second term. We can take that 4 that the log base a of 3 is multiplied by, and then we can put it inside the log, and now we have log base a of 3 raised to the 4th power. The first term, log base a of 7, doesn't change, not right now. So now, looking at the second term, we have 3 raised to the 4th power. That's 81. Now we have log base a of 7 plus log base a of 81. By noticing that they have the same base, they're added together. Well, actually, this is equal to the log base a of the product of those two terms, 7 and 81. Log base a of 567. And given that we don't know a, that's as far as we can take this in terms of simplification. Now let's look at another expression. Here we have 2/3 times the natural log of 8, and from that we're subtracting the natural log of 5 squared minus 1. The first term we want to take that 2/3 and place it inside the natural log expression. And now we have the natural log of 8 raised to the 2/3 power. The second term becomes the natural log of 24. When we simplify further, we see that the first term becomes 2 cubed, still raised to the 2/3 power, and the second term becomes the natural log of 2 to the third times 3. When we simplify again, the first term becomes 2 squared, natural log of 2 squared. The second term, we haven't done anything to it yet, so it's the same as it was in the last step. And then we can combine those two terms. They are the difference of two logs with both of the same base, and we can write them as a quotient. It's the natural log of the quotient. And that simplifies to be the natural log of 1/6. Simplify that by saying it's the natural log of 1 minus the natural log of 6. The natural log is actually equal to 0. From that, we subtract the natural log of 6, and minus natural log of 6 is our final answer.